Welcome back, grade 10s. In today's lesson, we are going to complete the section on longitudinal waves, and we will also go through some past paper questions. We arrived at pitch, loudness, and tone. Now remember that sound waves create compressions and rarefactions that enter the ear, and they get converted into electrical impulses, which are then transmitted to the brain, which interprets it as sound. Now, the human ear can't hear all frequencies of sound. Our ear can process between 20 hertz and 20,000 hertz. 20,000 hertz is also equal to 20 kilohertz. Anything less than 20 hertz is considered infrasound, and anything more than 20,000 hertz is considered ultrasound, but we'll come back to that later. Now let's talk about pitch. The pitch of a note is how high or how low the note sounds. So think of an opera singer that sings at a very high note, and that pitch is directly proportional to the frequency of the sound. So given two graphs, one with a higher frequency and one with a lower frequency, the one with a higher frequency has a higher pitch. A high-pitched note has a high frequency, and a low-pitched note has a low frequency. So, for example, the chirp of a bird has a high pitch, and therefore a high frequency. The roar of a lion has a low pitch and a low frequency. This has nothing to do with loudness. This is just how high or low the note is. In this case, we have a low pitch versus a high pitch. Their loudness is the same, and that is because loudness is directly proportional to the amplitude of the sound wave. Now, in this case, we can see a sound wave with a lower amplitude and a sound wave with a higher amplitude. This one is going to be a softer sound, and this one is going to be a louder sound. A soft note has a small amplitude, and a loud note has a large amplitude. So, for example, the chirp of a bird will be soft, so it will have a small amplitude, and the roar of a lion will be loud, so it will have a large amplitude. Pitch and loudness are very, very often asked. You need to know that pitch is proportional to frequency and loudness is proportional to amplitude. Let's now talk about the tone of the sound. Tone refers to the quality of the sound. The tone or the quality of a sound depends on its frequency, its amplitude, its timbre, and its waveform. You may think of timbre as the character of the sound. So, for example, if you play a trumpet or a keyboard or a vuvuzela, they all sound different. Each one of these musical instruments has different characters in the way that it generates the sound, and that is the timbre of the sound. So even if they have the same frequency and the same amplitude, the trumpet and the keyboard are going to sound different. The waveform represents the pattern of the sound wave over time. A high quality tone is pleasant to the ears. So that means that the sound waves are predictable and regular and they have a pleasant timbre. So music, the song of a bird, ocean waves, a gentle breeze, those sounds have a pleasant tone. A low quality tone is unpleasant. It is unpredictable. It is irregular, and the timbre is also unpleasant. Examples include traffic, construction work, sirens, a crying baby. Now, in terms of waveforms, this is a pure note. This is a single sound being generated. It's not changing. It's just one note. When it comes to musical instruments and to music, we want to generate not just one pure note, but we want to generate many different notes that come together beautifully, but they also have to be repetitive for the tone to be pleasant for us. And noise looks very random, and noise has a low quality tone. Let's now talk about ultrasound. Remember that we said that the human ear can only hear frequencies of sound that are between 20 Hz and 20,000 Hz. Infrasound refers to sound waves that have frequencies that are less than this value. This is the lower limit of human hearing. Now remember, this is a low frequency, so it's a low pitch. Ultrasound refers to sound waves with frequencies above the upper limit of human hearing, which is anything greater than 20,000 Hz. So that would be a high pitch, a high frequency sound. Now, us humans can't hear infrasound and we can't hear ultrasound. Many animals can hear ultrasound. So, for example, bats and dolphins are known for using echolocation to navigate the world around them. And they do this by emitting ultrasound sound waves, and that helps them, as we already discussed before, to locate prey, avoid predators. They can make an image of the environment around them based on the reflected sound waves that enter their ears, and they also use it for communication. Other animals that can hear ultrasound include certain species of whales, certain species of rodents, moth beetles, some snakes, some lizards, some birds. For example, owls and swifts can hear ultrasound. Dog whistles use ultrasound, so they emit high-frequency sounds above the range of human hearing, but within the range of dog hearing. So when the user blows into the whistle, it creates a sound that the dogs can hear, but humans can't hear it, and so it doesn't disturb nearby residents. Ultrasound is also widely used in medicine. Ultrasound creates an image by using a high-frequency sound wave, an ultrasound wave, that's emitted from a small device known as a transducer. The transducer sends sound waves into the body, and they travel through different tissues and organs, and they reflect back into the transducer at different speeds, depending on the different tissue densities that it has hit. The transducer then records the returning sound wave and sends them to a computer. The computer uses complex algorithms to process that data and create an image. The image appears on the screen and it shows a 2D or 3D view of the internal structures of the body. Now, because different tissues and organs in the body have different densities and structures, that will affect the speed and pattern of the returning sound wave that enters the transducer. So, for example, bones reflect almost all the sound waves, so they create a bright image on the screen, whereas soft tissue reflects fewer sound waves, so those images will not be as bright. And things that are fluid, like blood, they appear as dark areas or shadows on the image because they do not reflect sound waves effectively. So this is how an image gets created using ultrasound. And if you're asked what property of this ultrasound radiation allows doctors to view an image inside the body of a person, you would say that that property is reflection, because the sound waves get reflected off different tissues and organs, and they therefore create an image on the screen. By analyzing the ultrasound image, doctors can identify abnormalities in the body. They can monitor fetal development during pregnancy. Unlike X-rays, ultrasound is safe because it is free of harmful radiation. So, as far as diagnostic tools are concerned, ultrasound is preferred because it is very safe. Ultrasound is not only used in medical imaging, it may also be used to break up kidney stones in a non-invasive manner. So there's a machine called a lithotripter, and that generates a high-frequency sound wave that is directed at the kidney stones. This device helps to locate each kidney stone, determine the size of the kidney stone and the shape, and use that information to calculate the exact position and the intensity of the shock wave or ultrasound wave that is needed to break up the kidney stones. The shock waves pass through the skin and through the soft tissue, and they break the hard kidney stones into smaller pieces. And now these smaller fragments may pass through the urinary system. So here we can see kidney stones that are too big to pass through the ureter. And here we can see that ultrasound is being used to break them up into smaller pieces. And now they've been broken up into smaller pieces so they can pass through the urinary tract. The same idea occurs with gallstones in the gallbladder that can also be broken into smaller pieces that then allows them to pass more easily through the digestive system so that they can be excreted. Dental hygienists use ultrasound in a procedure called ultrasonic scaling, where they use a small handheld device that releases ultrasound radiation, and those vibrations break down tartar and plaque in the teeth so that it can be detached from the teeth and the gums. Ultrasound is not only used in the medical industry, this technology is also used in other industries. So, for example, ultrasonic cleaning uses high-frequency sound waves to loosen and remove dirt from surfaces of materials like jewelry and electronic equipment. Ultrasound is also used to detect defects in materials. So, for example, a crack in an aeroplane wing or corrosion of a pipeline. Instead of having to dig and identify where the defects in the pipelines are, ultrasound radiation can pick that up. Ultrasound technology is also used in the agricultural industry to detect defects in seeds and to determine crop quality. Ultrasound technology is also used in agriculture to measure the moisture content in the soil and to monitor plant growth. This brings us to general examples on longitudinal waves, specifically sound waves, and all of these questions come from past papers. A sound wave produced by a vibrating musical instrument is represented in diagram 1. Label the sections marked A and B. Now, A is just a point in space and B is a certain distance. A represents a compression, whereas B represents the distance from compression to compression, which is known as the wavelength. The position versus time graph in diagram 2 represents the same sound wave produced by the musical instrument in diagram 1. So here we have a sound wave that is represented graphically. Name and define the type of wave represented in diagram 2. Now, because it is a sound wave, we automatically know that it is a longitudinal wave. And remember that definitions need to be learned off by heart. So it's a longitudinal wave, which is a series of disturbances where the particles of the medium move parallel to the direction of the propagation of the wave. Which point or points on diagram 2 correspond to A and B on diagram 1? So remember that a compression is represented by the crest of the graph, and a wavelength is represented by any 2 points that are in phase. Now, B is specifically crest to crest. We don't have a crest to crest label here, so the only full wavelength that we have on this diagram is XZ. So A is Y and B is X to Z. The same note is now played on the instrument, but louder than before. How will this change affect the graph in diagram 2? What we know is that loudness is directly proportional to amplitude. So a louder sound would correspond to a larger amplitude. A note of the same original loudness is now played on the instrument, but the note is changed to a higher pitch and frequency. How will this change affect the graph in diagram 2? Now, we learned that pitch and frequency are directly proportional. But we can't simply say here that the frequency of this graph will be greater, because that's already given to us in the question. So when the frequency increases, what decreases by definition? What is frequency indirectly proportional to? And the answer is the wavelength. So the graph will now have a shorter wavelength. A sound wave travels to a high wall which is 225 meters away from the source and is then reflected. If the speed of sound in air is 340 meters per second, calculate the time it takes to hear the echo. In questions like this, it is useful to draw a diagram. We know that the speed of sound in air is 340 meters per second. Now the echo travels to the wall, which is 225 meters away, and then it travels back to the person so that they can actually hear that echo, which means that up front we can't just use a distance of 225 meters, but rather we need to take that value and multiply it by 2 in order to calculate the time that it takes for the echo to reach the person's ear. So the distance is actually 450 meters. Time is distance divided by speed, which is 450 divided by 340. So it will take 1.32 seconds for the person, once they've generated the sound, to hear the echo back in their ears. The same sound source is used to produce an echo by sending the sound wave into water. Is the time it takes to hear the echo less than, equal to, or more than that obtained for the question above? Remember that in denser mediums, sound waves travel more efficiently, meaning that they travel faster and they travel further. So the answer here would be less than. Sound travels faster in water than in air, and that is because water is more dense than air. Ultrasound is used in medicine. State the property of ultrasound wave that enables ultrasound to be used in imaging. And I already told you the answer to this when we discussed ultrasound, and the answer is simply reflection. Those ultrasound waves are reflected off tissues and organs and back into the transducer. Dolphins communicate through the emission and reception of sounds. A young dolphin was separated from its mother and started whistling at a frequency of 130 kilohertz to call her. The speed of sound in seawater is 1,480 meters per second. Now, immediately we need to see that we need to convert kilohertz into hertz. And what we've got here is the frequency of the sound wave, and we've got the speed of the sound in water. Firstly, what is ultrasound? Ultrasound is sound frequencies that are greater than 20,000 hertz. This does not need to be included in the answer, but frequencies greater than 20,000 hertz are inaudible to the human ear. Calculate the wavelength of the young dolphin's whistle. So we've got the speed and we've got the frequency. Therefore, we can calculate the wavelength of the wave. However, up front, we need to convert our frequency from kilohertz to hertz. So 130 kilohertz is 130 times 10 to the 3 hertz. Now we may apply this formula. Wavelength is speed divided by frequency, which is 1,480 divided by 130 times 10 to the 3, which is 0.01 meters. Another dolphin hears the distress call of the young dolphin 2 seconds later. How far apart are the two dolphins from each other? So now we're asked to work out the distance between the two dolphins. Remember that distance is speed times time. We were given the speed of the sound wave in water, and we know that the sound was heard after 2 seconds. So it's 1,480 times 2, meaning that the two dolphins are 2,960 meters away from each other. Compare the speed of sound in air and water. Well, all we need to state here is that the speed of sound in water is greater than the speed of sound in air. And if we ever needed to explain it, it would be because sound waves travel faster through denser mediums. So the speed of sound in air is slower than the speed of sound in water because air is less dense than water. How do dolphins use echolocation to hunt their prey? Dolphins emit ultrasound. They listen to the echoes that reflect back, and those would be the two key words. They use ultrasound, and then they listen to the reflected sound. Dolphins can identify prey and estimate the distance from the prey based on the time it takes the echo to return. And that brings us to the end of longitudinal waves and sound waves. In the next lesson, we will start on electromagnetic radiation.